So as we jump into our content for Module 12, looking at external flow, within this module we're going to focus on the problem of computing heat and mass transfer rates to or from a surface in an external flow. So in such a flow, boundary layers develop freely without constraints imposed by adjacent forces. So this will be the bulk of what we're going to be looking at within Chapter 7. Accordingly, there will always exist a region of the flow outside of the boundary layer in which velocity, temperature, and or the concentration gradients are going to be negligible. So that's something we want to pay attention to and see what we can consider negligible for these problems as we start them. Now examples include fluid motion over a flat plate, inclined or parallel to the free stream velocity, and also flow over curved surfaces such as a sphere, cylinder, airfoil, or a turbine blade. So now let's take a look at the objectives we're going to cover within this module. We want to take a look at the empirical method, then take a look and discuss the flat plate and parallel flow, moving on to the methodology for a convection calculation, looking also at the cylinder and cross flow, the sphere, and then looking at the flow across a bank of tubes, then moving on to our impinging jets and also packed beds. So these are the objectives and topics we're going to be looking at within this Module 12, related back to our textbook, Chapter 7. So now, as I've mentioned, we're going to break this module down into two different sections. We're going to look at Module 12.1 and Module 12.2. Within our first section, Module 12.1, we're looking at external flow and specifically looking at the flat plate and parallel flow. So within this module section here, 12.1, we're going to be taking a look at the empirical method, talking about this flat plate and parallel flow, where within that, what we're going to look at is laminar flow over an isothermal plate. We're going to look at turbulent flow over an isothermal plate. Then we'll look at mixed boundary layer conditions, moving on to unheated starting length. And from there, go to our flat plates with constant heat flux conditions. And then finally look at our limitations on the use of the convection coefficient. So we're covering all these different areas and scenarios within our flat plate and parallel flow. And last thing we're going to look at is the methodology for a convection calculation. So within this section, Module 12.1, we're taking a look, going over the theory for these above topics, discussing the governing equations, looking at some practical applications, and then going through my hand solutions to a couple problems. So as we jump into our Module 12 and we get into Chapter 7 in our textbook, we're taking a look at the flat plate and parallel flow. First section of this module for our 12.1, we'll be looking at this sections 7.1 through 7.3 in your textbook. So let's take a look now at our physical features. And we look at our diagram, we have on the left side of it our laminar flow, and the right side our turbulent flow. So we can see the total length of our plate here is our L distance here. And we have our distance in our laminar region defined here as our x sub c. And we can see here this is all moving in our x direction from our reference point here at the end of our plate. We can also see we have our surface temperature T sub s. And we have over here our ambient temperature T sub infinity and our U sub infinity as well. Now, as with all external flows, the boundary layers develop freely without constraint. The boundary layer conditions may be entirely laminar and turbulent, or entirely turbulent. So we can see that there. There's a little bit of that transition region where we have both that laminar and turbulent. So now in order to determine the conditions, we can use the following relationship shown here in order to compute. So we can see we have our Reynolds number is equal to, we have our rho times our U sub infinity times L all over our mu right there, where our rho is going to be our mass density. We can see our U sub infinity is our velocity times L, the length of the plate, all divided by our viscosity there. Now when we look at this here, we can see we have our mass density right here, and we have our dynamic viscosity right here. So we look at our relationship over here, where we have our kinematic viscosity is equal to the ratio of our dynamic viscosity divided by the density of the fluid right there. So if we have the inverse of this, we can say, okay, rather than rho over u, if it was u over rho, we would have our v. So now we have our kinematic viscosity on the bottom when we replace our rho over u right there. Now this reduces down to, now we have our mu sub infinity, or the velocity, times the length of the plate, all over now our kinematic viscosity here for this relationship. So now what we can do is we can compare this value here with the critical Reynolds number, which right here is our Re sub x comma c. That's our critical Reynolds number for our transition to turbulence. So right here we're transitioning into our turbulent region. So if this value that we get from our relationship up here is going to be less than our critical Reynolds number, then we have laminar flow throughout. But if the value from that equation above here is going to be greater than our critical Reynolds number, then the transition to turbulent flow at that distance here, we see x sub c over L, so there's our x sub c and there's our L right there, is equal to the ratio now of our critical Reynolds number all over our Re sub L right there. So now the value of our critical Reynolds number is going to depend upon the free stream turbulence and the surface roughness. So nominally, we have that our critical Reynolds number here is approximately equal 5 times 10 to the 5th. Now, if the boundary layer is tripped at the leading edge, then we have the case here where our critical Reynolds number is 0 and the flow is turbulent throughout. Now, our surface thermal conditions are commonly idealized as being uniform temperature, our T sub S, or uniform heat flux, our Q sub S double prime. We can also note that our thermal boundary layer development may be delayed by unheated starting length. So that's something you want to pay attention to, take a look, and if this is heated at the beginning of what the temperature is there, and if it is unheated, then again, this may delay that boundary layer development. So let's take a look at this diagram below. And what we can see is that we have our equivalent surface and free stream temperature. So here is our surface temperature, our T sub S, and our free stream temperature right here, our T sub infinity. Now, if our value here for X is going to be less than this distance right here, we can see that our surface temperature is going to be equal to our free stream temperature. So TS is equal to T sub infinity. But if our X value is going to be greater than this distance here and around here, we can now see that our T sub S, our surface temperature, is going to be greater than our free stream temperature right there. So TS is greater than our T sub infinity. So now I want to take a look at the similarity solution for laminar constant property flow over an isothermal plate. So we have this special situation here. Now, based on the premise that the dimensionless x velocity component, we have our ratio here of our u over u infinity, and the temperature, our dimensionless temperature T star, which is the ratio here between our difference in our T minus Ts over our T infinity minus Ts, can be represented exclusively in terms of a dimensionless similarity parameter. So this is our dimensionless similarity parameter right here, and this is equal to, and we can see this relationship from equation 7.10 on page 438 of our textbook. We have y times, we have our u infinity, all divided by our new x to the 1/2, where we can come back over here, double check what our variables are. X is our distance, u sub infinity is our velocity, and we can see that our new right here is our kinematic viscosity. So now this similarity permits transformation of the PDE, our partial differential equation, associated with the transfer of x momentum and thermal energy to an ODE, our ordinary differential equation, in the form shown down here below, which is related back to equation 7.17 on page 439 of our textbooks. We have 2 times, we have d to the third f all over d times eta to the third right there. So this is a third order ordinary differential equation. Plus now we have f times the second order ODE right here, d squared f over d eta squared is equal to 0. Where our u over u infinity is equal to the derivative of f with respect to eta, our df over d eta right there. And we have this following relationship now here from equation 7.21 on page 440 of our textbook. We have the second order ODE, d squared, our dimensionless temperature, T to the T star, all over d eta squared, plus our Prandtl number, PR over 2, times f times our first order ODE, dt d eta. So that's our partial of our dimensionless temperature with respect to eta there is equal to 0. So this relates back again to our equation 7.21 in our textbook. So now let's take a look at the similarity solution for laminar flow over an isothermal plate in this diagram below. So subject to prescribed boundary conditions, numerical solutions to the momentum and energy equations yield the following results for the x component velocity distribution and the temperature distribution in the boundary layer. So on the left-hand side over here in part A, we have the x component velocity, and we can see that right there. There's our u over our u infinity there that we saw previously on the other side. That is our definition for that dimensionless x velocity component. And then over here in our part B of our diagram, this right here is our temperature distributions for the given PR relationship here. So PR is equal to 0.6, 1, and 7. So what we can do is we can relate, if we go to part A right here, this dimensionless x velocity component on our x-axis here, to over here we have our eta term right up on the left side on our y-axis, where eta is going to be our dimensional similarity parameter. We see this is our eta over 5, which we can equate to our y over delta, which delta defines the boundary layer thickness. So we can see our y-axis on both of those is either our eta over 5, which is equivalent to that y over delta on our y-axis. Well, let's take a look now at the situation. We're at the edge of our velocity boundary layer. So we're going to have our dimensionless x component, our u over our u infinity here at 0.99. We have our eta term here at 5. So with that there, we can look at our equation 7.19 on page 439 of our textbook. We're looking now at that boundary layer thickness that we talked about in the previous slide. So our delta here, our boundary layer thickness, is going to be equal to 5 divided by this relationship here of our u infinity over our nu x to the 1/2, so we've seen that relationship before. So we can reduce that down a little bit and relate it back to our Reynolds number here. So this is 5x over our Reynolds number in the x direction to the 1/2 power. And this relationship is given for our boundary layer thickness in equation 7.19 in our textbook. So looking at this relationship in our equation 7.19, we can see that it becomes clear that our boundary layer thickness, our delta value, is going to increase as our x value and our nu value increase as well, which are our distance and our kinematic viscosity. So as those increase, this is going to cause our boundary layer thickness to increase as well. But it's going to decrease with our increasing value here for our velocity, our u sub infinity right there. So the larger the free stream velocity, the thinner the boundary layer is going to be. In addition, we can also find a relationship now for our wall shear stress, our tau sub s right here. So this is our wall shear stress for this relationship here. And this is given in the textbook as well in the same section as your 7.19 and your equation 7.15 as well. So we have the relationship here that we have our mu times our partial of u with respect to y, evaluated when y is equal to 0, is equal to our mu times our u sub infinity times the square root of the same relationship that we see up here, our u infinity over our nu x times our second order ordinary differential equation, d squared f over our d eta squared, evaluated when eta is equal to 0. So we have that relationship there, and we can see if we go back to our table 7.1 in our textbook, we also have the following relationship that we see here, that our second order ODE for our d squared f over our d eta squared, evaluated when eta is equal to 0, is going to be equal to the value of 0.332. So we can use this T sub s, our wall shear stress, in equation 7.20 on page 440 of our textbook in order to calculate the local friction coefficient. So we have this equation given here where we have our C sub f comma x, which is our local friction coefficient. This is going to be equal to, there's our wall shear stress in our x direction, all divided by our rho u sub infinity squared over 2, which we now have seen we have a relationship for that. We can reduce this down and simplify it, get it in terms of our Reynolds number here. So this could be equal to now 0.664 times the Reynolds number to the negative 1/2. So again, this relates back to our equation 7.20 in our textbook. Let's take a look at a couple of relationships relative to our local convection coefficient so that we can plug in to get our equations that we see in 7.23 and 7.24 in our textbook. So looking at our local convection coefficient, we have our h of x, which is that local convection coefficient, and this is equal to our heat flux, our q sub s double prime, divided by our temperature difference, our Ts minus T infinity, our surface temperature minus our surrounding temperature. Now this can be reduced down to our thermal conductivity times our partial of our dimensionless temperature with respect to y, evaluated when y is equal to 0. And then we can plug in for that, and this is going to be now our K value, our thermal conductivity, times this relationship that we see above up here from equation 7.19, which is u infinity divided by our nu x to the 1/2, times now we have our derivative of our dimensionless temperature with respect to eta, evaluated when eta is equal to 0. So let's just take a look at this portion right here. The derivative of our dimensionless temperature with respect to eta when eta is equal to 0. So we can bring this down here, and this is going to be reduced down to the relationship we see here of a 0.332 times our PR number to the 1/3 for values when our PR is greater than 0.6. So now this is all goes back and gives us a relationship for this local convection coefficient. So now that we have this relationship for our local convection coefficient, our h sub x, we can use that relationship to plug into our equation 7.23 from page 441 in our textbook. We're looking at our Nusselt number. So our Nu sub x is equal to, there is our h sub x, our local convection coefficient, times our distance x divided by our thermal conductivity. So now we go back up here and say, okay, what is our h sub x? Well, our h sub x from this relationship here is our thermal conductivity, K, times our u sub infinity over nu x to the 1/2. Now this relationship comes from up here from equation 7.19. We saw that this relates to x over our Reynolds number to the 1/2 power. So we can replace this portion of this with this relationship of x over our Reynolds number there, plug it in, and this is multiplied by our relationship for our partial of our dimensionless temperature with respect to eta, and we showed that this down here is equal to this relationship. So between this up top here from 7.19 and this relationship here, we can plug that all in and we can see that this, for our Nusselt's number, is now going to reduce down to 0.332 from this relationship here. There's our PR number to the 1/3 right there. Now this is going to be times our Reynolds number to the 1/2 using our relationship up there. So you can see what's canceled out is now we have our X and our K canceling out from that from our relationships from the previous example shown up here in 7.19 and from our relationship here for our local convection coefficient. Now as we move on to our equation 7.24, what we have here is a ratio of the velocity to the thermal boundary layer thickness given by delta over delta T is equal to our PR number to the 1/3, where our delta we can calculate based upon our equation 7.19 that we showed up here at the top, which is our boundary layer thickness. So now let's take a look at our average boundary layer parameters. So if we forego our local results, then our average boundary layer parameters can then be determined. So let's first take a look at our local friction coefficient. And for our average local friction coefficient, we have the relationship shown here from equation 7.29 in our textbook on page 442. We can see the bar right here. This denotes that it's an average right there. Our C sub Fx, which is that local friction coefficient, is equal to, now we have this relationship here of 1.328 times Reynolds number to the -1/2. Now we also have a relationship for our average wall shear stress. Our tau sub s comma x bar right there, where the bar denotes our average, and this is equal to 1 over x times our integral with the limits of integration going from 0 to x of our tau sub s dx. Then below we can see we have a relationship shown for our average convection coefficient. So our h sub x bar is equal to 1 over x times the integral, with limits of integration again from 0 to x, of our h of x dx, where again that h of x is our convection coefficient. Now with that, we can come up with our equation on page 442 of our textbook, equation 7.30 for our Nusselt number. So we can see our average Nusselt number here is equal to 0.664 times our Reynolds number to the 1/2 times our PR number to the 1/3. Next, I want to take a look at our variable properties. Now, these may be considered by evaluating all properties at the film temperature. So our film temperature, we have the variable T sub F, and this is equal to our T sub S plus T infinity, which is our surface temperature plus our surrounding temperature, all divided by 2. And this relates back to equation 7.2 in our textbook on page 436. Now let's take a look at the turbulent flow. So for our turbulent flow, first we'll look at our local parameters and then we'll move on to our average parameters. So for our local parameters, we have these empirical correlations. So we have this for our local friction coefficient and our local Nusselt number. So for our local friction coefficient, we have the relationship for turbulent flow. This is equal to 0.0592 times our Reynolds number to the -1/5. And for our local Nusselt number, we have this is equal to 0.0296 times our Reynolds number to the 4/5 times our PR number to the 1/3. Now for our average parameters, we have our H bar L is equal to 1 over that length L times, now in here we can see we have two different integrals. We're doing this for the laminar section and for the turbulent section here. So with this here, it's the integral from 0 to x sub c over our h laminar dx plus the integral from continuing on now where we left off at x sub c up to the total length L of our h turbulent dx. So this is for our average parameters there. So what we're going to do next is sub in the expressions for our local coefficients with the assumption that our critical Reynolds number is 5 times 10 to the 5th. So based upon that, we can come up with a relationship here for our average parameters still, for our average friction coefficient, and this is going to be equal to 0.074 divided by our REL to the 1/5 minus 1,742 divided by our RE, our Reynolds number, L right there. So same we can do now when we sub in these expressions for the local coefficients to our Nusselt number. So our average Nusselt number now given by this relationship here that's equal to 0.037 times our RE, our Reynolds number sub L to the 4/5 minus 871 times our PR to the 1/3. Now for the case, if our Reynolds number, critical Reynolds number is equal to 0, or our L, our total length, is much greater than our X sub C, then we have this relationship here where our Reynolds number L right here for our whole length here is much greater than at our critical Reynolds number right there. So this now gives new relationships for our average friction coefficient, average Nusselt numbers, shown by these relationships down here. So that does simplify these down a little bit. So our average friction coefficient is equal to 0.074 times our Reynolds number sub L to the negative 1/5, and our average Nusselt number is equal to 0.037 times our average Reynolds number sub L to the 4/5 times our PR to the 1/3. So it does simplify those down for the special case here where our critical Reynolds number is equal to 0. So now there are going to be instances where we have to deal with special cases. So let's take a look at one special case here. So for this special case, we have an unheated starting length, or USL, and or a uniform heat flux. And we can see we're going to reference back to the same diagram that we saw earlier. We have a flat plate. You can see our total length is X is equal to L. X is moving in this direction here. The beginning section, we have our TS is equal to T infinity up to this length. Then after this length here, we have our TS is greater than T infinity. So our T infinity is shown over here, and there's our U sub infinity as well. And we can see there's our heat flux right there for our uniform heat flux that we're showing within the special case. So for both uniform surface temperature, our UST, and uniform surface heat flux, our USF, the effects of our USL, or unheated starting length, on the local Nusselt number may be represented by the two following equations, shown as 7.42 and 7.43 in our textbook on page 445. So we have these two equations relating to those there, and I would recommend going back to that section of the textbook and look at how they derive these relationships. But we do have them here that you can reference back to if you need them for a certain problem that you're solving for this special case. So now let's dig in a little bit more detail to our UST, our uniform surface temperature, and then we'll do the same for our uniform surface flux, our USF. So for our UST, we have the relationship that our surface heat flux, our QS double prime, is equal to our HX times our temperature difference of TS minus T infinity, and our Q is equal to our HL bar, which we'll talk about in a minute, we already have a relationship for this, times AS times our temperature difference of TS minus T infinity, and our Nusselt number right here, our average Nusselt number, is equal to this following relationship here, where we have values for P in our exponent here. So for these P values, if we're dealing with a laminar flow throughout, our P is equal to 2. And if we're dealing with a turbulent flow throughout, we can use our P is equal to 8. So now looking at our H sub L bar, this is a numerical integration for our laminar turbulent flow. And we've seen this relationship before, where HL bar is equal to 1 over L times, now here's our integration for both our laminar and our turbulent section right here, our integral to X sub C of H laminar dx plus our integral from XC to L on the other side during our turbulent region of H turbulent dx. So now let's take a look at our USF, our uniform surface flux. So we still have the following relationships, that our surface temperature T sub S is equal to T infinity plus our surface flux, or Q sub S double prime, all over HX, and our Q, our heat transfer coefficient, is equal to our surface heat flux times our area. So these are all things that we've seen before, just recalling those relationships there when we're dealing with our uniform surface flux. Now, if we want to talk about the treatment of our non-constant property effects, we can evaluate the properties at our film temperature, and we recall a relationship for our film temperature that T sub F is equal to T sub S plus T infinity over 2. So now what I want to do is apply some of these concepts and governing equations to an example problem. So I'll be going through my hand solutions to this example problem 7.21. Let's take a look at problem 7.21. In this problem here, the top surface of a heated compartment consists of a very smooth A and a highly roughed B portions, and the surface is placed in atmospheric airstream. In the interest of minimizing total convection heat transfer from the surface, which orientation, 1 or 2, is preferred? So we have that TS is equal to 100 degrees Celsius, T infinity is equal to 20 degrees Celsius, and U sub infinity is equal to 20 meters per second. They want us to find the convection heat transfer from the entire surface for this orientation. So we can see down below, again, where A is very smooth and B is highly roughened, you have the two surfaces here. You can see all of our variables are given to us as well. Here's our T sub S for our surface temperatures.
Here's all of our dimensions as well. So we have all the information given to us either in the problem statement or in the schematic down below. So now that we've had a chance to read through the problem statement, the next step is to write down all of our variables, our knowns, what they're asking us to solve for, and any assumptions that we might make, along with a simplified version of our schematic diagram. So take a look at this problem here. What do we know? We know our TS, surface temperature, is given us at 100 degrees Celsius. Our surrounding ambient temperature, T infinity, is 20 degrees Celsius. U sub infinity is given to us as 20 meters per second. Our L is equal to 1 meter. Pressure is 1 atm. A is very smooth and B is rough when we reference back to our diagram here. So what are they asking us to solve for in this problem? They want us to find the preferred surface, either A or B, the very smooth or the rough, to minimize the total convection heat transfer from the surface. So what can we assume as we're going through the solution to this problem? What we can assume is that surface B is sufficiently rough to trip the boundary layer when in the upstream position. We can also assume that Reynolds number Re sub x comma c is approximately equal to 5 times 10 to the 5th for flow over A in configuration A, where A is that extremely smooth surface. So we can make these assumptions when we're going through our solution here. We can reference back to all of our knowns, what they want us to solve for, and our given diagram with dimensions and all our surrounding conditions. Now for the first part of our solution, what we want to do is refer back to table A4 for air. So when we go back to this table there, we'll be able to find our T average value here based off of our given values for T sub s and T sub infinity. So what we can do here is we can say, okay, I know my T infinity is given to me as 100 degrees Celsius, and I know my T sub s, my surface temperature, is 20 degrees Celsius. Add those two together, divide by 2, and we get a value of 60 degrees Celsius, or 333 K. So then we can take this 333 K for our average temperature value here, and we can plug this in on table A4 to get all the associated properties that we're looking for. So let's take this value of 333 K and take a look at table A4 to see where we get our properties. So now we can go to table 8.4. In our textbook, this is the thermophysical properties of gases at atmospheric pressure. So as we take a look through here, what we know is we found our average temperature. Our average temperature was by taking our surface and our ambient temperature of 100 degrees Celsius and 20 degrees Celsius, averaging them there and converting that to Kelvin. So we ended up with 333 Kelvin as our average temperature. So we come over here to our temperature in Kelvin. You see I've kind of written in red here our 333 for our value. So that's in between our 300 and our 350. So we'll need to do some interpolation. We're going to want to get our V, our K, and our PR number here. So we go through, do our interpolation, figure out our V at 333, figure out our K at 333, and figure out our PR at that same 333 Kelvin. And from these values here, double check, pay attention to what your units are. This is to the 10 to the 6th, 10 to the 3rd. Make sure you do that appropriately so you get the correct units as we plug in later. So now that we've had a chance to go to table A4 and look at our properties for our temperature, average temperature of 333 K, we can pull off our V, our K, and our PR values there. So when we do our interpolation, we'll roughly get that V is equal to 19.2 times 10 to the negative 6 meters squared per second. Our K value is equal to 28.7 times 10 to the negative 3rd watts per meters times Kelvin, and our PR is equal to 0.7. And again, we had to pay attention to our units that were given to us in this table to make sure we do it correctly with our values for these here. So with this information that we've gathered from table A4, our next step is to take a look at equation 6.23 in our textbook on page 390. So with this here, we have this relationship here. Now we have the R E sub L is equal to rho times U sub infinity times L over mu. And we recall here that we have this value over here with this relationship. So our V is equal to our mu over rho. So we can take this relationship that we have here, plug back in for this relationship here, which is the inverse of this. So if V is equal to mu over rho, then rho over mu is equal to 1 over v here. So if we replace this now with a v, we have this relationship here. So REL is equal to u sub infinity times L over v. So this eliminates a couple of those other variables that we may or may not have. It makes life a little bit easier for moving forward. So from this here, our next step in our solution is to plug in our known values for this here. Well, we have this is given to us in our problem statement. We can reference back to the first page where all our givens are, and we can plug in there that this is 20 meters per second there. Our L is also given to us as 1 meter, and our V is a value that we just looked up from table A4 up top here. So we got a value for V, which is 19.2 times 10 to the negative 6 in units of meters squared per second. So as you note here, I've wrote in all my units here so I can do unit analysis, make sure things come out in the right units and everything double checks. So we get a value here. So for R sub EL is equal to 1.04 times 10 to the 6. So for the next part of our solution, we're going to go to equation 6.24 on page 390 of our textbook. And this is to solve for our critical Reynolds number. So we're looking for our critical Reynolds number. We have this relationship here given by this equation 6.24. Rho times our u sub infinity times xc, location there, divided by our mu, is equal to 5 times 10 to the 5th. Now we can rearrange and solve for that location x sub c. And what we can also do is we can recall that same relationship here, that mu over rho is equal to v there. So we can replace this part of the equation with our v value here that we've already had from our lookup from table A4. So therefore our x sub c location is equal to 5 times 10 to the 5th times our v all over our u sub infinity. We know we have a value for v. We know we have a value given to us for our u sub infinity at the beginning problem statement. So we can plug in these known values for x sub c. So what we have here for x sub c is equal to 5 times 10 to the 5th times 19.2 times 10 to the negative 6 in meters squared per second for our value here for v from our lookup table. And we have our u sub infinity over here of 20 meters per second. We can see the meters cancel the square, the seconds cancel the seconds over here. We end up with a relationship here is just a meters. So do the top, this ends up being 9.6 over 20, which equals xc of 0.48 meters. Now, for configuration 1, the transition will occur just before the rough surface because of this x equals 0.48, and this distance, the dimension here at A, we recall, is 0.5. So for the next step in our solution, what we want to do is take a look at this mixed boundary layer condition. So we have the surface A and surface B, where surface A is smooth and surface B is rough. So where we want to start for this solution is to take a look at a governing equation on page 444 of our textbook. We're going to take a look at equation 7.38. So this equation is given as for a Nusselt's number here, 0.037 times the Reynolds number to the 4/5 minus A, all this times PR to the 1/3. Now we need to figure out a relationship for A. Where this comes from is from equation 7.39. On page 444 of our textbook there. And if we take a look at that, we get this relationship for A here, where A is equal to 0.037 times Reynolds number RE sub XL to the 4/5 minus 0.644 RE sub XL to the 1/2. So from this relationship on equation 7.39, we can then plug in our known values here. So we have a known value for our Reynolds number that's given to us the problem statement. We can plug in for both of those there. So A, when we plug that in, becomes 0.037 times 5 times 10 to the 5th to the 4/5 minus 0.644 times 5 times 10 to the 5th to the 1/2 power. Break this down, do all our powers there for the exponents, break it down again for each term, left side and the right side, combine these together, do the subtraction, and we end up with A is equal to 871. So remember now, this was just to get our value for A to go back to equation 7.38 on page 444 of our text to plug in for this relationship here. So we do that there, we plug that back into equation 7.38. So our Nusselt number here is equal to now 0.037 times the Reynolds number to the 4/5 minus, there's our A right there, 871 times PR to the 1/3. So now we do have a value for PR that we found before. We also have a value for our Reynolds number there. So we can plug these in now. We have that our Nusselt's number is equal to 0.037 times 1.04 times 10 to the 6, all to the 4/5 power minus 871. This entire thing times 0.7 to the 1/3 for our PR number there. Plug these values in, do it out, and end up with Nusselt's number, average Nusselt number, equal to 1,366. Next, let's take a look at the next condition here. We have a completely turbulent boundary layer when we're going over the rough surface here. So now we can reference back to page 445 and see for this condition here the Reynolds number XZ is equal to 0. Therefore, our A is equal to 0 for this completely turbulent boundary layer. So such a condition may be realized by tripping the boundary layer at the leading edge. So I would recommend that you head back to page 445 to look into this a little bit deeper on where these relationships came from. So next, what we can take a look at is back to equation 7.38 that we saw before. For the previous solution on page 444 of our text, we're looking for our Nusselt's number here. So now we're going to call this 2 for our boundary condition 2 that we're calling this here over the rough surface. We now are going to have this relationship here. So we plug back into that general equation where Nusselt's number is equal to 0.037 times Reynolds number to the 4/5 minus A times our PR to the 1/3. But based upon this condition from page 445 for a turbulent boundary layer, our A is equal to 0. So this A goes to 0, goes away there, which reduces and simplifies down this equation 7.38. So our Nusselt's number here for the second condition is equal to 0.037 times Reynolds number to the 4/5 times our PR to the 1/3. Well, now we can start plugging in our known values here. We have our value for a Reynolds number, we have a PR number here, so we plug that in, we get 0.037 times our 1.04 times 10 to the 6, all to the 4/5 times our PR of 0.7 to the 1/3 power. Plug those values in, we get Nusselt's number, an average Nusselt's number here for the second condition over the rough surface of 2,139. So what we can do now that we've done this for both the smooth and the rough surface, condition 1 and condition 2, between A and B, we can compare those two average Nusselt number values there. For the second condition, we have 2,139 over the rough surface, and the smooth surface was 1,366. So therefore, the rough surface is greater than the smooth surface, so therefore the longest heat transfer is associated with figure 1. So we're going to do the rest of our calculations for this problem based on figure 1, a condition for our smooth surface. So next what we want to do is recall again this equation here for our Nusselt number for position X here, which is equation 7.30 on page 447 of our textbook here. So this is equal to our average H sub X times X over K value there. Plug in the specifics for our problem for this now. So our average Nusselt number, so NUL comma 1, again for condition 1 that we're going with now, for our average HL for 1 times the length L given to in the problem statement divided by our K. And this is going to be equal to this 1366. We know that value from up above there. So we can rearrange now and solve this for our average H for this L comma 1. So we do that there, we rearrange, and this ends up being that 1366 times K over L will give us that value. We can plug in our knowns at this point here, plug that in there. We know our K value and we know our L value from the problem statement. This is from our lookup table here for K. So average H sub L comma 1 is equal to our 1366 that we found previous page here for our solution for our Nusselt number there, times our K value of 28.7 times 10 to the negative third in units of watts per meters times Kelvin, all divided by our L, which is in 1 meter there. Pay attention to our unit analysis. We get an average HL1 equal to 39.2 watts per meter squared times Kelvin. Those are the units we'd expect there. So this is our value now for our H.